Okay, in 1.6, we're going to evaluate limits algebraically. The easiest way to evaluate a limit algebraically is if the graph is continuous. If f of x is continuous at x equals a, the limit as x approaches a of f of x is the same as f of a. I'm going to sketch a random graph. Okay, this is my little graph. Okay, at x equals a, let's say x equals a is down here. I don't know where it is. Okay, if this graph is continuous, the limit as x approaches a is the same on both sides, and it's the same as the value of f of a. So if it's continuous, the easiest thing to do is just plug a in to get the y value at that exact point. So we call that direct substitution, and that's the easiest way to evaluate a function when possible, and it's often possible, so you need to check that first. Okay, so the limit as x approaches negative 3 of x squared plus 2x minus 4, we are just going to plug it in. Let's see, so that's going to be negative 3 squared, 9 minus 6 minus 4, which is negative 1. Okay, and once I plug in the negative 3, I stop writing limit as x approaches negative 3. Okay, so limit as x approaches 2 of 2 squared minus 1 over 2 plus 3. This is not actually continuous. It's discontinuous at x equals negative 3, but at x equals 2, it's fine, so I'm going to go ahead and plug it in. 2 squared is 4 minus 1. 2 plus 3, so I get 3/5. Okay, and if it was not continuous, you would be able to determine that, and I'll show you in a second why. Okay, let's see. Let's go ahead and plug in negative 6. If I plug in negative 6, what do I get? Numerator. I get 36 minus 24 plus 3. At the bottom, I have negative 6 plus 6. What is that? 12 plus 3 is 15 over 0. Now, 15 divided by 0 is undefined, which when we're talking about limits, we say the limit does not exist, or the abbreviation for the limit does not exist as DNE. Okay, now we're going to learn some strategies for when we cannot tell what's happening. Okay, now the first strategy is factoring and canceling. Okay, now I would like to do direct substitution. That's what I would like to do. So let me try that first. Okay, if I do direct substitution here, limit as x approaches 0, let me plug in 0. At the top, I get 0 minus 0, which is 0. And on the bottom, I get 0. Okay, now the problem is, if you get 0 over 0, this is what we call indeterminate. And it doesn't mean it doesn't exist. It means I just have no idea what it is, and I need to do more work to figure out the answer, because there is an answer there, but there's some kind of hole there. So if imagine a graph like this, there's a hole where x is approaching. So there probably is a limit. I just need to figure out what it is, but at the exact point, there's not a value. So the first strategy is factoring if possible. Okay, now I'm going to manipulate the algebra. So I need to keep writing limit as x approaches 0 until I finish doing that. In the numerator, I can take out the x. Okay, now I can cancel out these x's. This goes with this. Okay, now I can go ahead and try direct substitution. If I try that, I get 0 minus 5, so the limit is actually negative 5. So it does exist, it's just the value of f of 0 does not exist at that point. Okay, let me go ahead and look at the next one. Again, direct substitution is the easiest way to do it. I can see I'm going to get a 0 at the bottom. If I plug it in the top, 98, I'm going to get a 0 at the top because I already figured it out, 908. Okay, let me go ahead and factor it. Okay, I am going to keep writing the limit as x approaches negative 7 because until I factor it, I have not actually evaluated the limit. Okay, you factor using whichever method you like. Plus 7 minus 1. Okay, I can see the x plus 7 is going to cancel. Okay, and now I'm going to use direct substitution. So that's negative 14 minus 1, which is negative 15. And you are going to show your steps on these things, especially the algebraic steps, so I can see what you did. Okay, now we're going to introduce a special trig limit that you are going to memorize because it's a useful limit to have, and it allows you to skip some steps. We'll later learn methods where we can actually prove that this is true, but for now I'm just going to tell you what it is, and then I'll show you on Desmos. Okay, so the limit as x approaches 0 of sine of x over x. If I were to do direct substitution, the sine of 0 is 0. So this is 0 over 0, which is indeterminate. So I have no idea what it is. and there's not enough information. The same if I do the reciprocal, I get 0 over 0. It turns out that in fact the limit is going to approach 1. Okay, and I'm going to show you on Desmos real quick why that is the case. Okay, so this is the other special trig limit. The limit as x approaches 0 of 1 minus cosine x over x. Cosine of 0 is 1. So if I do 1 minus 1, I get 0, 0 over 0, which is indeterminate. And if I switch the order here, it's still 1 minus 1. So it's 0 over 0, which is indeterminate. It turns out that this actually equals to 0. And you are going to memorize it. And again, we'll find a way to prove it in the future, but we don't have those means yet. Let's look at the graph so you can at least believe that it's probably true by looking at the graph. Remember, this property only works when the limit as x is approaching 0. For each of these, some people remember this by looking at the word sine. Since there's an I in the middle, it looks kind of like a 1. For cosine, since there's an O in the middle, it kind of looks like 0. Okay, so let's go ahead and look at these right here. Now, if I plug in 0 here, sine of 0, 0 over 0, it's indeterminate. It looks like I should use this property up here, but that 3x is throwing me off. So I need to make this look like the property. Now, if this were sine of 3x over 3x, then I could use this the property because it's a sine of something over that same something. So let me rewrite this so that it matches that, and then I will fix it to make it work. Okay, now I want it to be the sine of 3x over 3x because I know that that will equal to 1. However, I can't just like randomly put this 3 here without balancing the equation. So since I randomly did put this 3 here, I'm going to go ahead and put a 3 up there so that they cancel out. Okay, now this expression is the same as this expression because if these 3's canceled out, it looks the same as this. However, I can evaluate that green part. The sine of 3x, the limit as x approaches 0 of the sine of 3x over 3x is 1, which means this is really going to be 3 times 1, which is 3. Okay, we're going to go ahead and do the same thing on the next one. And again, it's the x approaches 0, and I'm going to get 0 of 0, which is a mess. If I could get this to look like this, I could evaluate. So if I had sine of 7x over 7x, that would work really well. So I'm going to kind of make it what I want it to be and then adjust it so that I didn't do anything algebraically illegal. So I want it to be the sine of 7x over 7x because that I know is going to be 1. Now what do I do with that 9x? Now I want this to be the sine of 9x, but that means I need to have a 9x here. Okay, now I randomly put the 7x and the 9x here, which is not good because I just completely messed up the equation, so I need to balance it out. Okay, now let me see. Now since I put a 7 on the top, I need to put an extra 7 at the bottom, or 7 at the bottom, I need to put a 7 at the top. And I put an x at the bottom, but I actually already put an x at the top, so that's okay. Now I put this 9 at the top, so to balance it, I need to put a 9 at the bottom. Okay, now this is the same expression as the original expression because this cancels, this cancels, this cancels, this cancels. But this is going to be easier for me to evaluate because the limit as x approaches 0 of sine of 7x over 7x is 1. 9x over sine of 9x, 1 times 7/9, which means that the limit of the original expression is actually going to be 7/9. Okay, let's look at the last one. Now for C. Now if I were to plug in 0, the cosine of 0 is 1. 1 squared is 1. 1 minus 1 is 0. At the denominator, I'm going to get a 0 when I plug in 0. So this is a problem. It looks like the numerator factors, so I'm actually going to try to factor it first and then go from there. Okay, and I'm going to keep writing limit as x approaches 0 until I've actually done the direct substitution step. Okay, that's a difference of squares at the top so that I can make that cosine x plus 1, cosine x minus 1, and I'm going to write out the steps to show that I have not done anything illegal. Okay, now I can cancel the cosine x plus 1 with the cosine x plus 1. So let's bring down what I have left now. I still have cosine x minus 1 in the numerator, and I have the x in the denominator. Okay, now actually this now looks like this. So using the property, I know that this must equal to 0. Okay, so I went ahead and graphed y equals sine x over x. From the graph, just looking at it, I can tell that as x is approaching 0, the y value is approaching 1. So just looking at it, it seems to confirm what I think to be true. We will prove it at a later point. Now let's look at the other trig limit, and then I'll switch back and show you the graph to show you that it appears to be true. Okay, so I went ahead and graphed y minus cosine x over x, which makes this graph right here. The limit as x approaches 0. Here's x is 0. It looks like it's approaching 0 on both sides, so which is y the limit as x approaches 0 if that expression is 0. It's not a proof, but it does seem to confirm the property.